Hello there. I'd like to welcome you all to Chapter 3. Chapter 3, which is our chemical bonding.
We'll start this chapter with a demo called Fast Rusting. What we have in this jar is iron scale, essentially some iron flakings made from you heat metal. It partially oxidizes, but it's still, as you can see, highly magnetic. It's sticking to this neodymium rare earth magnet, one of those rather small button magnets you can buy from the store. See how the scale is all black and attracted to the magnet. Well, so now I put the scale with the magnet on the outside, magnet on the outside, the scale on the inside, and I'm pouring concentrated acid into the flask. The purpose of this is to remove any protective oxide layers from the iron. As I pour it back out, I'm going to then plug this this bottle and then invert this bottle with a straw into some just food coloring dyed liquid, and we're going to see what happens. Now, what we should see happen is that iron, now unprotected by the oxide layer, should begin to rust. As it begins to rust, it's going to create a suction that's going to draw up the fluid, up the straw, and into the flask. And as it does that, the iron rusts. It's going to turn from our black to brown, and it's going to lose some of its magnetic properties. Because the straw is submerged in the fluid and no oxygen is allowed to enter the flask and replace it, as the iron rusts, we're creating that vacuum, which is in turn sucking the liquid up that straw further. See, it's rather high up that straw pipette at this point. The iron is thoroughly rusty.
We can already see our beautiful black iron is now turning brown and rusty.
As we see here, the iron has lost a lot of its magnetism. There's still mildly magnetic, as it's not fully rusted. The outer layer may be rusted, but there's still some iron core in there that is left unrusted, which is helping it stick. But as we see, it's a lot more sluggish to move around. Some of it will still be attracted, but not the whole chunk like it used to be. And that is the fast rusting. It did not rust anymore overnight. Let's get on with the chapter.
Now, we started Chapter 1 by looking at electrolytes and looking at sodium chloride. So, we saw how that when sodium chloride salt is dissolved in water, it has all these properties of breaking up and conducting electricity. But let's look at just the pure elemental versions where sodium metal, chlorine gas, how very different these guys are from the compound version that we saw, that is our table salt. Sodium solid rusts very quickly. It will oxidize naturally in air, and so much so that we have to store it under oil to prevent overreaction. And if you drop it in water, it will actually explode. Small chunks will just fizz and pop, while large chunk the size of a walnut will explode violently because it's going to release hydrogen gas and form a base, and it produces a lot of heat. Of course, we know hydrogen plus a spark means big boom, as we talked about with the Hindenburg. Sodium in its pure elemental form is no actual known, no common uses of it in its elemental form, except for, I guess, southern style fishing. Now, chlorine gas can be a disinfectant. It's very, very reactive. We use it. We can disinfect water supplies in small quantities. We can use it to disinfect swimming pools. But in large quantities, it's highly toxic, and it was actually one of the poison gases used in World War One. It was released. It's a mildly greenish gas that's heavier than air, and released from bottles, it would blow with the wind across the battlefield and into the trenches, where it would cause horrible burns to the face and lungs unless people were wearing gas masks. And so it was very dangerous and very terrifying. But sodium chloride, on the other hand, is quite safe. I mean, the worst sodium chloride leads to is hypertension, which in itself is not exactly a good thing, but compared to the fact small quantities of chlorine gas will kill you, small quantities of sodium solid can kill you, small quantities of sodium chloride is safe. That's sometimes the difference between looking at an ion versus a pure atom. And the thing of it is, there's no set rules. You can't say, well, the ionic form is always dangerous and the ionic form is always safe and the atomic form is always dangerous. It's really a case by case basis. If you look at nitrogen, it's over 70% of our atmosphere. It's relatively unreactive. Oxygen, we need that to breathe. Sure, it helps fuel fires, but we need oxygen to breathe. But NO2, a byproduct of automobiles, is one of our key pollutions, can generate nitric acid in the acid rain that's in the air, which, when breathed in, can cause serious harm, can destroy various buildings as acid rain deposits dissolves stone, among other things. Not saying that nitric acid isn't a good thing in certain situations, but when in the air, definitely not so. So, ions, it all depends on really the usage here. Properties can be affected by atomic weight. It can also be affected by mass number. Just look, plutonium is pretty much deadly in all forms, which is why it was often used as a assassination means. You have a little plutonium pellet, you stab someone with an umbrella surreptitiously, depositing a plutonium pellet, they die several days later, painfully and publicly, as they die of radiation poisoning. Not really any cure to radiation poisoning. Atomic mass, as I said, could be a big thing. Water has H2O with protium as the main H. Water, as we know, sure, you can have a water overdose, called drowning, or drink far, far, far too much water and go into like electrolyte shock. But water in itself is relatively safe. But if you make it deuterium, heavy water, it becomes dangerous and quite fatal. So the little change of a neutron could be all the difference. And one of the main ways that 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 the properties are going to differ is based on the electronic structure, which is where we're going to focus the majority of this class. The electronic structure has a large control of the reactivity, especially when considering the valence shell of electrons. The valence shell, of course, is the outermost quantum shell. All the inner shells are technically called the core electrons, and they don't really react. The valence electrons are the electrons in that outermost valence shell, and those are going to be because it's usually like in a job, usually the last in are the first out. So these guys are going to be the guys that are going to be you're going to put electrons into the valence shell, you're going to take electrons out of the valence shell before you touch any of the innermost shells. And to understand this, there's a way to simplify. We can simplify our electronic structures by looking at Lewis structures or electron dot structures, which they're simply structures showing the elemental symbol and the valence electrons arranged in paired or unpaired dots. So we're just showing the valence electrons. This was brought about by Gilbert Newton Lewis, over as you see here. Rather interesting gentleman. He started in Nebraska, went to grad school in Massachusetts, and studied in Germany under Walter Nernst. Guy, among other things, famous for theoretical chemistry and like a theoretical physical chemistry and electrochemistry. If you go into more chemistry, you'll hear about the Nernst equation. But he really didn't enjoy it, and he went back. He left Germany bitter and went back to Massachusetts for a while, which he also didn't like. So he fled to the U.S. Philippines, where for a couple years he worked for the U.S. government, and he published papers nitpicking small errors that his predecessor Nernst had made. So he's kind of a jerk. Eventually, he went back home to California, where he went to UC, where he started work at UC Berkeley, and he built the chemistry program into one of the best chemistry programs in the world. Now, Lewis was one of the is probably the most famous chemist never to win a Nobel Prize, partially due to his naked ambition, partially due to all the disputes he made. That essentially a Nobel Prize is part science, part popularity contest, and when everyone hates you, it's kind of hard to get the votes. Plus, a lot of his science was broad, not deep, and that he did a lot of stuff over a lot of different fields, but none of it was so life-changing in any given field as to warrant that Nobel Prize. Besides Lewis structures, he did a lot of work with acids. He known for Lewis acids and Lewis bases that are electron donors and electron acceptors rather than the simple proton, hydrogen H plus, and OH minus that we commonly associate with acids and bases. And to make matters worse for him, while he helped during World War I and made some serious contributions for the government, he was passed over for the Manhattan Project in World War II, despite many key scientists in Berkeley that he helped form the chemistry department of joining the Manhattan Project. He would later die alone in his lab. It says he died of cardiac arrest, but his lab smelled of bitter almonds, which is a key feature of cyanide. And while he worked with cyanide, he could have simply dropped the cyanide vial while undergoing a heart attack, but he was also, as I said, very, very bitter, and he skipped going to a lunch with one of his comrades from UC Berkeley who was recently nominated for the Nobel Prize for the work in the Manhattan Project. So he was a not very happy guy in the end. Now, what one of the properties of this will show when we look at some of these Lewis structures is a periodicity of these elements. Periodicity that we see that elements of certain Lewis structures, elements with certain number of valence electrons, will tend to react in the same way. They will all display the same reactivity. You see that when we look at the noble gases, neon, argon, krypton, xenon, all of these guys are inert gases. They all contain 8 valence electrons, which is where we get the octet rule. The octet rule simply states that the atoms will react in such a way as to obtain exactly 8 electrons in their valence shell. The only real exception to this is helium, and that's because the valence shell of helium can only hold 2 electrons. But so that means so sodium has 1 valence electron. It will tend to lose 1 valence electron so as to get to the nearest noble gas, which would be what, neon. Let's see. Potassium has 1 valence electron. It will also lose 1 electron to get to argon. We have fluorine. Fluorine has 7 valence electrons. It will gain 1 valence electron and jump to 8 to get to be just like neon. Chlorine will want to gain one electron to get to 8, like argon. So we have this thing here that we can see. Now, this was all put together into our periodic table by Dmitry Mendeleev, pictured below. Now, while he is the best known inventor of the periodic table was actually invented by 6 people separately, independently. But one, he did more work with that, and he has a much better backstory. So there's a lot of things that why we know Mendeleev for the father of the periodic table, and not people like Lothar Meyer and other people. First, just like any good like like America's Got Talent show, having a good backstory will keep getting you through. He was born in Siberia, the first of the youngest of 14. He lost his father at the age of 13, and after his mother lost her job at the factory because the whole factory burned down, she bundled him up and rode 1,200 miles across the Ural Mountains to try to get him enrolled in college because he was so smart. They took him to Moscow, which he was denied entry to because he wasn't from Moscow. Then they rode another 400 miles to enroll him in St. Petersburg, where his father had originally attended university. She died not long after that. He studied a lot of different places, eventually came back to work at St. Petersburg. And over time, he worked under Bunsen, the guy known for the Bunsen burner. But he was that's where he started to work on the nature of elements. And so that was just reason number one. He's probably the one we think of. Reason number two is he was the one who realized the consistency of atomic weight, that while the elements may combine and lose various properties, like when you mix oxygen gas with a solid metal, you lose the gassiness of the oxygen, and you may lose some of the properties of the metal, but the one thing that stayed the same is the atomic weight. The atomic weight is the average masses of all isotopes weighted for their abundance of each. But so this atomic weight stayed the same. So we didn't gain mass or lose mass, we just combined the masses together. Or the third thing is he placed the elements in rows and columns. So people were able to place them in small little groups based on reactivity. And in fact, the early Nobel Prize that he and Lothar Meyer shared, which was called the Davy Medal, was only on the periodicity that these elements react the same. He was actually able to put them in order in rows and columns. And not only was he doing that, he was constantly revising the table, and he predicted new elements prior to discovery. Lothar Meyer, one of the other scientists working on the table, did not have, let's just say, the chutzpah to go ahead and say, this is the element, here's what the density should be, here's what the atomic weight should be. The table, and what makes matters even more important, his table was able to easily incorporate the noble gases once they were discovered. So it didn't suddenly fall apart when suddenly someone found neon, as we saw last chapter, or someone found helium. He had a place that he could put them on the table. In fact, what finally cinched the deal was when the discovery of gallium, which was originally called eka aluminum by Mendeleev. He even had the gall to name what the elements should be. So gallium was discovered by Paul-Émile François Lecoq de Boisboudron, and he found that and he named it gallium after France. Some people say he named it gallium you're not supposed to do this. You're not supposed to name an element after a living person, especially it's really poor taste to name it after yourself. But some people think since Gallia means the rooster and he is Lecoq, so he could have named it over himself. And basically Mendeleev got into various different fights and arguments with him, saying like, "Well, I discovered this," and Mendeleev was like, "No, but I predicted it first." And they were fighting back and forth. Eventually, Mendeleev once goes and points out that Lecoq had had misreported the density and atomic weight of gallium, and to Lecoq's great shame, he did do that wrong, and he had to retract his paper and fix his values and re-report them. The fact that a theoretical chemist was able to know more about the element than the discoverer of that element was what really probably sealed the deal. Now, while this Mendeleev was not perfect, he had plenty of errors. It's the fact that he had all these things kind of come into all together that made him stand out from everyone else. Let's look at some mass, how to calculate the atomic weight of certain common elements. Start with boron. Boron has two major isotopes, boron 10 and boron 11. Boron 10 is 19.78% abundant. Boron 11 is 80.22% abundant. This actually deviates greatly from every other atom. Almost always, the lighter isotope is often more abundant. However, in this case, the heavier one is. So to calculate the atomic weight, we're going to take the atomic mass of the isotope times the percent abundance and sum them up. So 10.0129 times 0.1978 gives it a contribution of let's say 1.981. And then 11.00931 times 0.8022. Okay, so when I sum these guys up, 1.981 plus 8.832, we get a mass of 10.813, which is the atomic weight of boron. Not 10, not 11, but 10.8. This accounts for the fact that there's some boron 10 and some boron 11. We'll go ahead and do one more. The book shows you how the chlorine was calculated. I'll go ahead and show you how bromine is calculated. This one is quite unlike most other elements in that both isotopes are about 50% abundant. So, calculating the contribution of each isotope, 3 times 0.4946. Add these guys together, and you get 79.91. Essentially 80. Essentially 80. A little bit less than 80, but right, just about as close to on the money as we can get. So even though we say the molar mass of bromine is 80, it's actually because we have a 50-50 shot of getting 79 and 81. So the average comes out halfway between the two. Now, so as he placed these elements, into families where all elements within a given column, and periods, all elements within a given row of the periodic table. So while it may not look it, lithium and beryllium are in the same period as boron, carbon, nitrogen, oxygen, fluorine. One of the key features here is that you could place them partially based on atomic weight, but really they're placed on atomic numbers. What makes this even more impressive is that atomic numbers weren't discovered till 1913, at like a good 20 years after Mendeleev's death or so. So he was very much so correct on a lot of assumptions, which you cannot really, you'd kind of miss if you look at some of these elements. Some of these elements is like, oh, some of the masses it's obvious, some of these not so easily obvious. That, for example, cobalt and nickel have actually, cobalt weighs more than nickel. Based on the periodic table, you would say cobalt should be 28, nickel's 27, but he was able to place it correctly based on what palladium and platinum were. And as I said, he knew where elements should be based on reactivity. Some of these are groups that we kind of should know. Like the first column is alkali metals, and second column is alkaline earth metals. These guys are so named because of their tendency to form bases, which is an alkali, a base, when mixed with water. We have things like the halogens over here. Hals, meaning salt or sea in Greek, because their tendency to form salts, being salts. And the noble gases over column 18 over here, that the noble gases are above everything. They don't really react. So all atoms will tend to want to react to get to these 8 electrons. So if you count your way across, ignoring these transition metals, we have 1, 2, 3, 4, 5, 6, 7, 8. As we look at this periodic table, we'll see certain things. See, sodium wants to lose 1 electron to get to a noble gas below it. Chlorine will want to gain 1 electron to become like a noble gas above it. Now, this reaction, if you mix sodium and chlorine together, you actually have a very explosive reaction. It's going to burn intensely bright when this does this. But it doesn't have to be with just sodium chloride. This will be true for all group 1 and all group 7 compounds, or as the table saw last, 17. But group 7, which is all halogens and all alkali earth metals, will do this reaction. And they'll act the same. Now, we can ignore francium and astatine. They are very uncommon. But if you go through lithium, sodium, potassium, cesium, let's see, is there another one? Rubidium. I always forget rubidium. They all act the same. Fluorine, chlorine, bromine, and iodine all act the same. And when they do this reaction, they form a ionic compound. Ionic compound is just a compound composed of ions. When we name this guy, we name it with the cation first and the anion getting an IDE suffix. This IDE lets us know it's gone from a neutral metal to a anion. So we can look at the charges. We can look at the charges of these guys. We could say that sodium could gain 7 electrons, or chlorine could lose 7 electrons. But the idea is that charges will repel, and the repulsion would be too strong on these guys. So it's always going to go to the closer side. In oxygen is 2 elements away, has a valence number of 6. So it's 2 elements away. And so it will want to gain 2 rather than lose 6. Nitrogen is valence number 5. It's 3 elements away. It'd rather gain 3 than lose 5, just because a smaller charge means lesser repulsion, means more stable. Now, these ionic solids, these ionic compounds, when they form, they will form a crystal structure that will actually form what's called a lattice, a crystal lattice, which is an orderly 3-dimensional arrangement of the chemical particles that make up this crystal. Basically, the positive will sit next to the negative, will sit next to another positive, and a repeating pattern that will go up, down, left, right, front, back in such a way to keep all positives away from all other positives and all negatives away from all other negatives. And it forms nice little crystals like this. When we zoom in to the atomic level, it looks more like this. This is a space-filling model. But as we actually draw the crystal structure and try to draw a unit cell, which is the repeating pattern, you can draw it kind of like this. This structure here is just this crunched together. But so you can see sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, chlorine. So there's no chlorine adjacent to any other chlorine. And this crystal structure is all made up of ionic bonds, which are just simply bonds resulting from the attraction of these oppositely charged particles. So these are held together by this electronic attraction. But when we add water, water is able to slip between these atoms and pull them away one by one, so that these ions, which are only held together by magnetic attraction, essentially, are able to separate and spread out through water. These charges can then be used to help conduct electricity through solution, thus allowing it to be electrolytic. Sucrose also adopts a crystal lattice structure. However, these crystal lattice, instead of being held together by ionic bonds, are held together by weak intermolecular forces, which we may discuss later. So when the water breaks them apart and dissolves them, there is no ions present in solution. It remains a molecule, just like water is considered a molecule. And these molecules have a defined chemical formula that includes no ions. So a chemical formula is just a sequence of chemical symbols and subscripts that shows that elements present in the compound. And if it's an ionic compound, it shows the ratio of their ions within the lattice, or it shows the actual number of the atoms within a given molecule. So in the crystal structure back in the last slide, we saw that there's hundreds of thousands of sodiums and hundreds of thousands of chlorines. But the idea is that for every 1 sodium, there's a chlorine. So if we see the ratio, it's a 1-to-1 ratio. But within a molecule, they have a defined number of each atom. So it's actually really important to look at that chemical formula. Now, within chemical formulas, we can have really complicated chemical formulas, or we can have simple binary compounds. Binary compound is just a compound made of 2 elements. Those guys are really easy to name. Now, for any binary compound, especially one made of ions, we will write the cation first. That's almost always a metal, followed by the anion, almost always a nonmetal. And we give the anion the suffix IDE. So NaCl becomes sodium chloride. If I had BaCl2, it would be barium chloride. If I had Na2O, you would have sodium oxide. So we're just taking the elemental name and adding an IDE and changing the suffix to tell it's an anion. If it's a molecule containing carbon, typically these are not binary compounds, but they can be. We'll look at this more when we look at organic chemistry later, but we label them carbon first, then hydrogen, and then all other elements in alphabetical order. So with glucose, you would have C6H12O6, since it's just carbon, hydrogen, and oxygen. But in more complicated molecules, you might have nitrogen as well. You might have sulfur. So you have to put them in alphabetical order as we go our way through. Now, as I said, cations with group 1, group 2, and with most anions, we're going to look with group 6 and group 7 are the most common anions we'll see. There might be some others we'll see later, but for now, we'll just start with those. Let's have a couple examples of that. Let's look at how we turn chemical formula into name. So, looking at these examples real quick, we look at first the cation. The cation, being from group 1 or group 2, just simply gets the name. So it becomes recognizing. Na is an unusual one, coming from Greek of like, I'd say natrium, but Na is sodium. So sodium. The O is oxygen, but in a anion, we remove the suffix and replace it with the IDE. Now, oxygen we remove a little bit more than the other elements, but that has to do with the prefix, the how it was named, oxygenes, begetter of acid. So we're keeping the oxy, but and replacing the gin with IDE, so it becomes oxide, sodium oxide. Ca is calcium. F is fluorine. So we replace the INE with IDE, fluoride. Make sure we spell that right. It's not flour, it's UORID. Ba is barium. And then S is sulfur, so it becomes sulfide. Rb is rubidium. And then Cl is chlorine, so it becomes chloride. I'll maybe do one more example. Al is aluminum. And oxide, aluminum oxide. Now, all the group 1, group 2, and aluminum, like kind of group 3, we don't have to really worry anything about specifying the number. That's already put to us in the formula. All we have to do is name the cation and the anion. That's how we'll name most standard ionic compounds. We might get into more clever ways to name them later, but for now, we're just starting with that. Now, when trying to actually predict how they'll combine based on the name, we need this simple fact. We need to remember that for a neutral ionic compound, the total charge of all cations must equal the total charge of all anions. So when we will look to our group number to help figure out what the charge should be. And then by using the fact that the cation subscript times cation charge must equal the anion subscript and anion charge, we can figure this out. So remember, we're looking to the valence number, which signifies our combining power. It's because valence comes from the Latin valentia, which means vigor or capacity. So like group 1 has a valence number of +1. Group 2 has a valence number of +2. If you have a group 3 like aluminum, it's often +3. Group 6 would have a valence number of -2 because it would need 2 electrons to make it 8. Group 7 would need 1 electron to make it 8. Group 5 would need 3 electrons to make it 8. So let's actually see some of these in action. Let's look at these guys. So cesium, when we think of cesium, we look to the periodic table. When we look to the periodic table, cesium is in group 1. Group 1 metal. So I'm going to put a 1 over this guy. We'll put a 1 below this. Iodine. Iodine is a group 7 non-metal. We have our valence. So 7 to get to 8, we have to add 1. So the number is 1. 1 to get to 8 or 0, we have to remove 1. So this guy's 1. So 1 times X equals 1 times Y. The subscript for cesium must equal the subscript for iodide. So they have to be the same. We're always going to use the smallest numbers we can. So this one just becomes cesium iodide. CSI. Magnesium. That's a group 2 metal. So we have 2X. Bromine is a group, bromide is a group 7. So it's a 1. 2X equals 1Y. The only way that would work is if when X is 1, Y is 2, meaning our formula must be MgBr2. Potassium oxide. Potassium, when we look at the periodic table, it is under group 1. When we look at the periodic table, oxygen is in group 6. Group 6. Now that means potassium is 1, and oxygen, to get to 8, must add 2. So we have 1x equals 2y. We have the opposite situation as the last one. The only way 1x is equal to 2y is x must be twice the size of y. So we have K2O. And aluminum. Aluminum is group 3, and chloride is group 7. So that means this guy is 3x equals 1y. To make that work, you would have to have AlCl3. So that's how you determine the coefficients. Now, if you're looking at what is the charge of a metal that we don't know, how do we figure this out? Like, say you have a chemical formula. You have a chemical formula and you're trying to figure out what is the charge of a metal. We're going to use the reference point, the anion, to let us know. The example they give us in the book is PbO2. Pb is group number 4, but we don't really know what that charge is. We can guess, but we don't really know. But we do know that oxygen is 6. Oxygen is 6, so that's definitely 2. The coefficient is definitely 2. 2 times 2 is equal to 4. And the coefficient there is 1 times, I'll say A, or alpha, is equal to 4. So the charge on lead must be 4. That seems really obvious there. But what about in the case of iron? Let's say iron, FeCl3. Iron is group, if you look at the table, it's group something like, I'd like to say 6. But it's definitely, and chlorine is group 7. Because they repeat, there's like 6A, or it's a transition metal. You don't have to, it's definitely not 6. That in mind, 1 times 3 equals alpha times 1. So the charge on iron must be 3 plus. To match 3 times 1 equals 1 times 3. One more crazy one. Let's see. Let's do Cr2O3. Chromate. Cr2, what? Well, chromium oxide. Well, we don't know what chromium is, but alpha times 2 equals 2 times 3. So chromium must be 3 plus. 3 plus on chromium. It's not always easy to figure that out. We have to think about these. Most transition metals have more than one possible charge. So you must consider this when you're looking at the name. When we looked at water, we said water was a poor conductor of electrons. The reason why water is a poor conductor of electrons is because it contains mainly covalent bonds. Now, a covalent bond, unlike an ionic bond, is a bond consisting of a pair of electrons which is shared between two atoms. It's shared rather than freely given as to make a charge. When we have these covalent bonds come together, we form a molecule. You will often see this covalent bond shown as two lone pairs a lone pair of two electrons placed between two different elements, or as a dash between them. We don't need a crystal to understand them. There can be simply a molecule. Now, the actual definition for a molecule is a discrete chemical structure that's held together by covalent bonds. When we look at hydrogen gas, H2, that's a molecule. When we look at CO2, that's carbon dioxide, that's a molecule. All these guys are made up of covalent bonds. Now, when we look at these molecules, they will have a molecular formula, which is simply the chemical formula of a covalent compound. Now, the molecular formula and chemical formula differ in one major aspect. The chemical formula simply refers to the formula of a chemical, whether ionic or covalent. The molecular formula really only refers to a covalent compound, because this looks at the exact number of atoms rather than a ratio of atoms. And within that molecule, you will have a molecular weight, which is simply the sum of all atomic weights of all the atoms within a molecule. I'll quickly show you how to calculate that real quick, but we won't really utilize this to some later chapters. Now, how do we calculate a molecular weight? The weight of a molecule. Say we have a molecule like CO2. How do we calculate that? We go to the periodic table. We look at the atomic weight. The atomic weight. Carbon is about 12. Oxygen is about 16. There's 2 oxygens, so we have to add 16 2 times. When we add 12 to 16 plus 16, 16 plus 16 is 32. 32 plus an additional 12 is 44. That would be the weight. 44 AMU with 1 molecule. I want something heavier. Let's go back to our sodium oxide again. Sodium oxide. Well, I don't think we did sodium oxide, but we'll go with sodium oxide. Sodium is 23 from the periodic table. There's 2 sodiums, so we have to double the 23. Oxygen is 16. 46 plus 16 is going to be 62 AMU. We can do this with any possibility. Let's look at glucose. Will be last one. C6H12O6. So there's carbon is 12. 12 times 6. Hydrogen is about 1. 1 times 12. Oxygen is 16. 16 times 6. So 12 times 6 plus 12 plus 16 times 6 is a weight of 180 AMU. That is the molar weight, molecular weight of glucose, the simplest sugar. Now, when looking at molecules, most nonmetals will be our covalent molecules. Hydrogen ends up being the maverick that is not placed with the other nonmetals that is often acting as a covalent bonder. Now, when we treat HCl, even though HCl should be covalent, it is very, very different from looking at pure chlorine and hydrogen gas. HCl happens to be a very reactive. It is our hydrochloric acid that dissolves lots of things, has lots of reactivity, as opposed to chlorine gas, which is relatively neutral, even though it's toxic, and hydrogen gas, which is relatively explosive, but still very much so neutral. The difference between these guys has to do with electronegativity, which is the measure of an atom's ability to attract the electrons of a covalent bond toward itself. Now, the thing of it is that chlorine is very electronegative. Hydrogen is not so. When chlorine is mixed with other chlorines, it's like a tug of war. You have 2 buff guys pulling against each other. Because they're both equally buff, no one really wins. And so the electrons stay in the center. If you have hydrogen, they're like 2 wimpy guys on that same rope. They're both equally wimpy. Rope doesn't go one way or the other. But when you have a wimpy guy on one side and a buff guy on the other, the rope's going to start moving towards the buff side. And so the more electronegative atom is going to pull the electrons towards that atom. And this is going to form a polar covalent bond. Now, this is a bond formed when the shared electrons of a covalent bond lie closer to one of the atoms rather than the other. And when this happens, we're going to form something interesting. We're going to form a dipole. It's the result of a separation of a positive and negative charge within a molecule. It's not a full negative and full positive. It's a partial negative and a partial positive. So it's not quite as strong as an ionic bond, but it's stronger than a standard covalent bond. When we look at these dipoles, they're represented by the Greek letter delta, the small letter D. It looks like a curvy D. This in this tug of war makes water a weak electrolyte. Water is a weak electrolyte because as we think of the bonds in water, they are covalent rather than ionic. So they don't really break apart much. The same thing is true technically with HCl, hydrochloric acid. In the gas phase, when we think of the bonds, they are covalent. However, that is not always true. That is because when we mix HCl into water, we have what's called ionization, where we produce ions. We're going to break apart along this dipole bond to make this into an ionic situation. And in fact, water in itself can break apart into from H2O to 1H plus and 1 OH minus, which is hydroxide and hydrogen ion. Now, normally in standard water, there is a small quantity of H plus and OH minus. But for every one pair of H plus and OH minus, there's something like 556 million unionized water. To make this ratio of ion to non-ion out of sodium chloride, it would be like dissolving 5 grams of sodium chloride into 850,000 liters, which that's about 225,000 gallons. To better picture that, so look at our football field. It'd be like you filled the water in the to cover the entire football field 7.5 inches deep. That's how much water you would need to dissolve 5 grams of salt into in order to get that same effect of H plus and OH minus. So by itself, water is a very poor electrolyte. But when we mix in things like acid or ionic compounds, you get really strong electrolytes, which is where we'll eventually see some reactions will be represented by an equilibrium. Looking at reversible reactions, equilibrium is when we have an arrow that goes one way and then can reverse back the other. The most common situation is H2O breaking apart into H plus and OH minus. This is reversible. On the other hand, when we have HCl, it's usually a one-way street, H plus and Cl minus, and that it is too hard for this to reverse back to its original starting point. There's many situations where we can have reversible reactions, like NO2. 2 molecules of NO2 can react to form 1 molecule of N2O4. But this can break apart. It all depends on the pressures and temperatures that this can go one way or go the other. And so we will sometimes see reversible reactions as we proceed through our class. In the beginning of this video, we looked at how iron can be turned into iron oxide, into rust, that the properties are very dissimilar between iron and oxygen in itself, that iron is magnetic, iron is strong, rust is weak, it's brown, it's flaky, it's non-magnetic. Oxygen is very reactive, it burns in the air, it's very gassy, but all this has come from the electron exchange in valence electrons. We know this because we've done this experiment. When we look at how do we know any given thing in chemistry, we got to remember chemistry is an experimental science, that we ask questions, we interpret the answers so that they make the most sense. From here on in this book, we'll look at various tests, various questions that have been asked throughout the ages and how we've gone about answering them, and how this has led to shape our current worldview. So I'm going to leave you with our writing prompt for today. I want you to try to make an observation about the world today. Come up with a hypothesis, and I want you to discuss how would you go about scientifically testing your hypothesis. What would you do? Post that up on the discussion board for people to read. See, what do you want to do? It doesn't have to be necessarily chemistry related, but what fact of our world can you make an observation about, determine a hypothesis of why this happens, and see about proving or disproving this hypothesis. So 150 words, come up with that. You can't have things like, well, I'm going to fly over here. You have to, something that could be done if you had enough money. You can't be Superman, but you can pretend you have an atom smasher or the money to run an atom smasher if that's what we so need. Okay. So, well, I'll see you again for chapter 4.